Okay, so this is our second lesson looking at bridges and analyzing trusts specifically. They don't have to just be in bridges, I suppose, of course. But what we looked at last time was something called the method of joints. And that's where we go to every specific pin and we're going to decide then we need a free body diagram, and that pin has to be in equilibrium. So we look at everything that's pushing and pulling on that pin, and we go from pin to pin to pin and try to figure out what's happening there. And we work out every single joint. Okay. And if you have something complicated, you're going to have a lot of joints to do. Okay. Now, it might turn out that you actually don't need to know what's happening with every single piece. Okay. And that's where this next method comes in very handy. And this is called the method of sections. Okay. The method of sections. Okay. Now, this word section, you're probably thinking about, oh, well, I've got a section over here and a section over there and a section over there. Yeah. That's true. But you need to think like a section is also a mathematical term for a slice. Okay. So if you go into an MRI machine or a CAT scan or something, they section up your body. They take little tiny pictures of it. So they're cutting up your body virtually so they can look at all of these little slices, and then they look section at a time, analyze each section to see what's happening inside your body. Okay. So what we're going to do when we say the method of sections is something similar to that. We're going to cut this thing, okay? And by cutting it, then we're dividing it into sections, and then we can analyze the sections to figure out what's going on, all right? So let's take a look here. It says determine the force in the members BCCF FE. State if they're in tension or compression. Okay, so let me get my highlighter here and we'll take a look at it. So BC is this guy. CF is this guy. And FE is this guy. Okay. Now, what we're going to do here is we're going to cut this piece in half. That's our method of sections. And we're going to cut it right through here. Okay. Now, of course, this is a virtual cut. It's a mathematical cut, not an actual physical cut. And what that's going to do is it's going to give us two pieces. All right. So let's take a look at both of those pieces. So I'm going to have a piece here. All right. And I'm going to draw it like this. And then we'll have another piece and it'll be here. Draw that here. Okay, now if I can get my little drawing program to work properly, what I should be able to do, oops, well, that didn't work at all. Okay, well, I was trying to grab the blue piece and the green piece separately, but I didn't want to have any part of that. Let me put that back. Pause my recording for a second. Okay, well, that took much longer than it should have, but I end up with what you can see here. Here's one side, and then here's the other. Okay, now in future videos, I'm not going to mess around with that. You'll know exactly what I'm talking about. Okay, so anyway, what we're going to do is we're going to cut these pieces like this. Okay, now, if an object is in static equilibrium, which this is statics, and so that's what we're talking about, then every piece is in static equilibrium. All right. So the left hand side and the right hand side, they're both in equilibrium. All right. Now, for the whole object, we're going to have the we have the external forces, the 600, the 600, and the 800. Then we're going to have the reactionary forces. And I've already worked that out. So G is going to be here like this. And so AX is going to be up here. And AY will be here. Okay. And let me just write down what those are going to be. All right. G is going to be 4,200. And I got that by basically putting a pivot at A and knowing that my 600, 600, and 800 were all going to be pulling the thing down. So G is the only thing keeping it from falling over if we put our pivot at A. Now AX has to match it. AX is also going to have to be 4,200 because G and AX are the only horizontal forces. Okay. And then vertically, we've got the 600 down, 600 down, 800 down. Only AY is up. So AY is going to have to be 2,000. Okay. So just like with the method of joints, we have to get those support reactions before we can go any further. Okay. All right. Now we got them. So I can get on with my what I was going to try and say. And so with the method of sections, what we're going to do is we're going to say, hey, I've got G here, and we know what it is, and I'm going to have an AX here, and I know what it is, and I need an AY here, and we already know what it is. But on this specific left-hand side piece, then we're also going to have the external force here. Okay. And then we're going to treat the internal forces as if they were some external force or some reactionary force. So we might call them an internal reactionary force or something like that. All right. But basically, what that means is we're going to need something in here. We'll call that BC. And we're going to need something here. And we'll call that FC. And then we're going to need something here. We'll call that FE. Okay. So now I've got three new forces that are acting on the left side of that piece. All right. And so my goal is to find out what's FE, what's FC, and what's BC. Okay. Now let's talk about choices before we get to the algebra part, choices of direction. Okay. So G and AX are equal and opposite. Okay. So they just automatically cancel each other out. So all we really need to do is think about FE, FC, BC, and the 600 as we're thinking about directions and the AY. Okay. So AY is 2000. Then I got the 600. So I knew that FC had to have some downward component because it's the only other force that could have any downward contribution. All right. Now, if we've guessed backwards and said FC is up this way, then our answer would have come out negative, and then we know, oh, we guessed wrong. Okay, we'll try again. Okay, now then BC and FE, just make your best guess about those. With some experience, you'll get better at kind of working those things out. Okay, now I did use my experience, and that's how I got BC pointing in that particular direction. Okay, and it was really kind of a guess still. All right. Now, with our other piece, the blue, what I've drawn is the blue one there. Okay. Let me get rid of that. Okay. Make it just a little bit bigger here like this. All of those forces that we've just drawn are going the other direction. Okay. So FE is pulling away from the joint F. That means that piece is in tension as we have drawn it. So that means FE over here is going to be this way. FC also is pulling away from F, so it's in tension. It's like a spring that's been stretched out, and it's pulling on each end. So it pulls that way there, and it's going to pull this way over here. BC, however, is under compression. So it's a spring that's been squished, and it's pushing outwards both ways here and here. Okay. And then, of course, we've got the external loads. Whoop, I want to keep my color codes consistent. 600 there, and then we had what is that one? 800, just like that. Okay. Now we can work with either side, the left side or the right side. So um, in the solutions to the fundamental problems in the back of your book, they choose the right side. So I'm going to do the left side for you. But what you should do after you watch this video is you should go using the fundamental solutions thing as your guide, do the right side and make sure you get the same answers. Okay. Because that's going to help you understand the technique and go through one of the problems. Okay. So, but for us now, we are just going to work on the left-hand side. Okay. So let me take a look at what we've got here. Okay. This gives me a little bit better view of the whole thing. Okay. So this is one of the things to look for is when you have something like the point F. Okay. Point F is right here. And FC goes through F, its line of action goes through F. FE goes through F. G goes through F. The 600 going down goes through F. Okay. So, of my three unknowns, I can eliminate two of them algebraically if I consider the moment around F. Okay. Remember, we're going to be looking at summing x's, summing y's, and moments. Okay. In any order we want to, in any way that we want to. Okay. So let's do that first. Let's take a look. We're going to sum the moments around F. Okay. So here's our point F right there. Okay. And oops, that's not what I wanted to sum the moments around F. We're going to set that equal to 0. Okay, so AX is at a distance away of 4. Okay, so you'll need to look at the picture. I'm not going to scroll down right now just to do that. And it's counterclockwise, so it's going to be positive. So I've got plus 4AX. And then AY is also a distance of 4 away, talking about its line of action, but it's negative. It's clockwise, so I got minus 4AY. And then I've got BC, and BC is also going to be clockwise. So I'm going to put minus 4 BC is equal to 0. Okay. Just going to check all my numbers here. Okay. BC is negative. AY is negative. AX is positive. Very good. Okay. Now we already know AX and AY. We've got those numbers. Boom, boom, boom. Pop out our answer. BC comes right out of there, 2200. Okay. So that's pretty straightforward. All right. Then what we can do is just pick either to look at the vertical or the horizontal forces, either one. All right. So let's do the vertical ones. Okay. We'll do the vertical ones because we've figured out this one. We don't know FE. FC is the only one with a vertical component to it. Okay. So let me draw a line here and come over here. And we're going to look at the sum of the forces vertically. And we're going to have AY up. And we're going to have the 600 down. Okay. And then the other force we have down is FC. And then let's say, I don't know, I'll do it as a sine of something. is equal to 0. So now we got to figure out, okay, was sine of what? Okay, and so we really need this angle up here. And if you look through the geometry, that turns out to be 45. Okay, so that's easy to get our hands on there. Okay, again, we know AY, we know 600, we know theta is 45 degrees. Okay, and so that tells us that FC, once we go through all of that, oops. Okay, here we go. I apologize for that. Lots of interruptions here today. And now my dog came to say hello, so I got to say hello back. Hi there. All right. Um, okay, so I think I was about to write down what we get there for FC, and um, FC is 1979.9, which your book is going to round up probably to 1980 or something like that. Okay. All right. Now we just have to get one more. All right. So far, we've got FC and we've got BC. We just need to get FE. And so the easiest way to do that is going to be to go ahead and look at the horizontal, the um, aspect of the forces. Okay, and scoot that over a little bit. So we're going to have AX here, and then we've got minus BC, and then we're going to have FC cosine 45, and that is in the positive direction, plus FC cosine 45. And that's equal to 0. Okay. And we know AX, we know FC, and we work all that out. And BC turns out to be, I'm sorry, BC is the one we know. I'm having one of those days. You guys ever have days like that? It's just like, are you kidding me? Are you kidding me? Are you kidding me? So here we go. We know FC. What we're trying to find is Fe, which I forgot to write in my equation. Okay, so let's erase this stuff here. There we go. Okay, and Fe is going to be in the positive direction, plus Fe is equal to 0. Okay. We know AX, BC, FC. Now we can find Fe. Okay. And once you do that, then FE that you're going to get is 800. Okay. Let me zoom out and let's kind of give that a flyby again. I've been rattling off a little bit. I apologize if this seems a little disjointed. Okay. All right. So this is the method of sections. What we're going to do is we're going to make a mathematical slice through our truss. Every component in the truss must be in equilibrium. So if we mathematically slice this thing, all the leftover bits must be in equilibrium. Okay. So once we find the reaction forces, we can slice this thing up and then we can treat the internal forces as if they're a sort of an internal reaction force. And we can solve for those using sum of forces and sum of moments. Okay. So let me just get my highlighter out here. Okay. So we cut it. Okay. And we looked at this side here. And we've got our unknown forces, Fe, Fc, Bc, like so. And so by putting our moment at F, we eliminated all of the unknown forces except for BC. And so BC popped right out. Then we looked at the vertical aspect of the forces acting on our part. And then we looked at the horizontal aspect of the forces acting on our part, and everything popped back in. Okay. So what I need you to do is duplicate what we've done here for the right-hand side. Okay. And you can use the solutions to fundamental problems in the back of your book as a sort of guide, and that's going to tell you if you got it right or not. Okay. Now, they do use a trick in which when they sum their moments, all right, they do one around one point and then they do another one around a different point. Okay, now that's something we haven't done before. So far, we've just been like, pick a point and stick to it. But you don't have to. Okay, there's no rule that says you only have to have one pivot point. You can use multiple pivot points. Okay, and so if it looks like that's going to save you some algebra, use it, do it. Absolutely. Okay. All righty. There we go. We made it through this first one. The next ones will go a lot smoother. That's my phone rings and blah, 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 blah.